Hello and welcome. I'm Alex Fuerst, and I'm going to be talking about our paper, Cloud Scale VM Deflation for Running Interactive Applications on Transient Servers. This was a joint work with Ahmed, Ali-Eldin, and Prashant Shenoy from UMass Amherst, and Prateek Sharma from IU Bloomington. So, transient computing has been receiving increasing amounts of attention. These cloud offerings allow providers to sell surplus cloud resources at discounted rates to customers as low priority virtual machines or VMs. There are many offerings of such VMs, including AWS spot instances, Azure batch VMs, and Google preemptible VMs. The downside from these cheaper VMs is the unexpected revocation or preemption of the VM and its resources when the provider reclaims the resources to make room for a traditional on-demand VM. Preemptions lead to application failure and possible downtime, making them poor and not ideal for interactive and long-running applications. In this presentation, we seek to answer the obvious research question of how can cloud providers offer low-cost and low-priority VMs without the worry of preemption for their consumers? So our answer to this conundrum is for cloud providers to offer deflatable virtual machines. These low-priority VMs avoid preemption by having their resources, CPU, memory, network, and disk bandwidth, fractionally reclaimed instead of wholly revoked. The VMs are kept running and can continue to make forward progress, but with a reduced resource allocation. As new VMs are created on physical hosts, low-priority VMs are deflated instead of preempted to make room sufficient to start the incoming VM. Note that deflation will only happen when there is resource pressure. Otherwise, deflatable VMs behave exactly like conventional VMs. And of course, these traditional on-demand VMs are not affected by this new deflation of their neighbors. So deflation comes with some significant benefits for all around, but some noteworthy trade-offs. Its black box solution supports all application classes, meaning that applications don't need to have expensive fault tolerance code or handle downtime scenarios that are necessary with current transient VMs. With these benefits come better availability, allowing interactive applications to consider running on transient resources. Cloud providers will be able to increase cluster utilization and reduce surplus resources, knowing that the cluster can handle higher load without needing additional hardware. The trade-off lands on applications, as they risk possible performance degradation if their internal utilization exceeds their possibly reduced resources. So to show the efficacy of deflation in cloud environments, we need to ask two questions. How amenable are typical cloud VMs to such deflation? And how can deflation be incorporated into existing public clouds? So next, we'll take a look at a trace-based look at typical cloud VMs deflatability, followed by examining how deflation is implemented at the server level and is managed at the cluster level. Then we have a variety of experiments showing the success of deflation, and we'll wrap up with related and future works. So we're going to first look at what is the performance impact on typical cloud VMs and how is this computed. So VMs, or deflatable VMs, will naturally suffer under allocation, where its resource allocation is below the original maximum allocation. So this scenario is shown here on the right. The figure depicts the VM's resources in blue as they rise over time, and above the deflated allocation, which is given here in red. Such under allocation at a time of high utilization is when performance degradation occurs. We can use these graphs to compute the impact or lost allocation above the red line on the VM as lost work throughput. In the inverse, if the VM isn't using resources that were deflated, we have just reclaimed slack resources, and it will suffer no performance degradation because it wasn't using these resources to begin with. So this information will tell us how amenable typical cloud VMs are to deflation. And we do this by analyzing usage traces from two top-tier cloud providers, Azure and Alibaba. First, we look at how much CPU resources can be deflated by. So the Azure trace gives us time series data of CPU utilizations per VM, along with useful metadata such as application class and VM size. We can then use this to see what fraction of time a VM's usage is above various deflation thresholds, which is equivalent to the chance a deflated VM will be under resource pressure and suffering performance degradation at those thresholds. So our analysis shows that interactive VMs are in fact highly deflatable, with the highest CPU utilizers only being impacted 20% of the time at a high 50% deflation. More common transient VMs workloads of batch VMs are also very deflatable, with 75% of them being impacted only 30% of the time at similar high deflation levels. It is our presumption that interactive VMs are highly amenable to deflation because they're over-provisioned already to handle possible peak loads and offering large amounts of slack at other times. So next, we move on to the Alibaba dataset and to examine the memory and I/O usages of their cloud container data traces. So on the surface, we found comparatively high memory allocations, but under further examination, we found that these applications were primarily JVM apps, which are eagerly hoarding heap space. So this is confirmed by comparing against the memory bandwidth utilization, where the average usage is roughly 1%. Such low utilization indicates these containers are not reading or writing in proportion to their memory allocations, and that their memory is still highly deflatable even if the static usage is high. So the Alibaba dataset also recorded negligible disk and network I/O bandwidth usage, making them both easily deflatable as well. So our analysis shows that the resource utilization makes low priority deflatable VMs a feasible offering in cloud environments. So VM deflation requires the ability to dynamically adjust the resources allotted to each VM. So modern hypervisors expose interfaces to monitor and modify these allocations. In these next slides, we'll examine how we use these interfaces to implement two classes of deflation: transparent mechanisms, which transparently shrink the VM's resource allocation, and explicit mechanisms, where the deflation is performed in a manner visible to the guest OS. Modern virtualization environments now support the ability to explicitly hot plug and unplug resources from running guest operating systems. Such allocation changes are therefore explicit to the guest OS and visible to any applications within it. Hot unplugging resources allows the OS to rebalance internal applications to handle increased resource pressure. However, hot unplugging does have some limitations. It must be done in coarse-grained units. For example, you can't unplug 1.5 virtual CPUs. And too much unplugging can cause instability and failures inside the VM, placing a limit on how many resources can be reclaimed this way. Lastly, NICs and physical disks are generally unsafe to hot unplug, requiring hypervisor mechanisms to deflate those resources. So if the guest is unable to hot plug the needed resources, then we must rely on the hypervisor to reclaim the remainder of required resources. So in this example here, the guest OS will be aware that these two virtual CPUs and a segment of memory were unplugged, and it can handle accordingly. So the hypervisor ultimately controls deflation events and allocations, using traditional VM overcommitment mechanisms to do so. So virtual CPUs can be multiplexed to fewer physical cores, memory pages can be swapped out, and network and disk bandwidths can be throttled appropriately. So our implementation of these mechanisms relies on KVM virtual machines running inside Linux C groups, which throttle the various allocations and CPU shares. Transparent deflation unfortunately does add overhead because it may reclaim resources that are being used by the applications, such as swapping out memory pages that contain important application data. So we combine these two mechanisms into what we call hybrid deflation. to take the advantages of both. The graceful handling from OS hot unplugging and the fine-grained slicing of transparent deflation. We reclaim what we can via hot plug until we hit the VM's safety limit, where resources the guest does not unplug. The hypervisor transparently multiplexes to make up the remainder. So here, after transparent deflation, our guest OS doesn't know that its virtual CPUs have been time sliced, some memory has been paged out, and the bandwidth for one of its NICs was throttled. So now, we'll look at how those mechanisms can be used to implement deflation policies at the physical server and cluster-wide levels. So VMs are deflated only when needed, but unfortunately resource contention does exist in the real world. So in this example here, we have a server with no available resources sufficient to take this incoming VM, but it has been directed to try and start this new server. So we can't simply preempt one of our low priority VMs because we want to make sure they're always running, but we still need to make room. So that leaves us with the question of how much do we deflate each low priority VM by? So the simple solution is to reclaim equal shares in proportion to the VM's original size, preventing small VMs from losing too many resources. So each deflatable VM is deflated proportionally to their maximum possible size of max sub I. The size of the new VM, which is equal to the amount of resources to be reclaimed R, determines how much each VM will give up, given alpha. We then compute for each deflatable VM how much resources will be deflated. All of them have their own X sub I, and shrink them accordingly. And it is worth noting that the incoming VM may also be deflatable, and if so, it will be included in this deflation calculation. So we can then expand on this simple proportional deflation by assigning each VM a priority, or a pi sub I. So in the simplest case, these can be set by the user based on VM price, resource usage, or application quality of service requirements. So VMs which have a lower priority are deflated more than VMs with higher priority. And this still ensures that VMs, that a sufficient number of resources are reclaimed for an incoming VM. So the priority also helps maintain a minimum allocation so that it will always have a set amount of resources. The minimum prevents the VMs from being deflated too much and suffering serious quality of service issues due to severe underallocation. And lastly, as VMs exit or are removed, their resources are naturally freed back to the hypervisor. So they can in turn be used to reinflate the other co-located VMs on that server. And reinflation is easily computed as the inverse of deflation, passing a negative R sub free as the R in the previous equations. So what decisions at the cluster level are made to place VMs, given that each placement will affect the deflation on those servers? So VM placement will affect deflation on overcommitted servers. So we want to make sure we carefully choose our placement strategy. So conventional placement uses bin packing to choose the right server. But with deflation, our cluster manager can track the overcommitment on all of its physical servers in the cluster. And when a new VM is scheduled, it can use this knowledge to intelligently pick a host with deflation-aware bin packing. It can also partition the physical servers and assign deflatable VMs to them, to each partition based on the deflation priority. This is convenient because it can help avoid the noisy neighbor effects on on-demand VMs or higher priority deflatable VMs. Deflation or bin packing is different from classic bin packing only when all the servers in the cluster have insufficient resources to handle a new VM request. So it will tabulate the still deflatable resources of low priority VMs, given here in green, to take into consideration. So the top server in this example has several VMs which can be deflated but still have all of their original resources. But our bottom server is already overcommitted with several VMs that do still have deflatable resources. So we must account for both deflatable resources and existing overcommitment when we make our choice. With all that in mind, how do we pick a server? We need to make this decision. So the various available resources, CPU, memory, and I/O on each server are tracked in availability vectors of AJ. So these are computed from a formula that takes the total physical server resources and less the ones that are already committed to VMs. So it then adds the still deflatable resources from its VMs, scaled by the server's existing overcommitment. We can then compute the cosine similarity fitness of placing the VM on each server based on that VM's requested resources, or D. Then the best fit algorithm chooses the server with the highest fitness to place it on. So we've conducted several testbed experiments and simulations to show the efficacy of deflation in the cloud environment. So our experiments seek to answer two important questions. First, how does deflation impact the throughput of interactive applications? We test this by locally running Wikipedia, a highly interactive web application, and its dependent services to test. Its tech stack has a lot of things in it, which is important. It contains a MediaWiki front end, a MySQL database, memcached for in-memory cache storage, and an Apache HTTP server. These were all run in KVM, as was described earlier, and then load is applied, loading the largest web pages as we deflate each VM. Our second question, we ask how well does deflation reduce the chance of preemption in overcommitted clusters? To do this, we created a cluster simulator with our server level deflation policies and the cluster level deflation-aware VM placement in it. So the VM utilization trace data from Azure is run through the simulator, with VMs being started and stopped corresponding to the trace data. And then the deflation of each VM is tracked over their lifetimes, so we can examine cluster-wide under allocation along with the number of preemptions that occur. So our interactive Wikipedia application doesn't see much degradation until it is under very extreme levels of deflation. So even at a very high, 70% deflation, the mean response is still less than 1/10 of 1 second, which is well below what most humans are noticeable under things like general web browsing and such. Only at extremely high levels of 80 or 90% do we see significant time impacts, and also we start having requests being dropped by the server. Now the simulation. This works by pre-computing the ideal cluster size for the peak resource usage of the Azure trace, and then we can over time shrink the number of servers to create artificial cluster overcommitment. So then we calculate throughput loss by finding the amount of time VM's resource utilization is above their resource allocation. So from all of this, we see that there's very little throughput loss caused by under allocation in the simulation. At the extreme case of 80% cluster overcommitment, proportional deflation causes just over 4% throughput loss. This loss is even less for both priority and proportional at a high overcommitment level of 50%, both of which are less than 1% throughput loss. So We believe this performed so well because the VM priorities were distributed according to their 95th percentile CPU usages, which we substituted as a quality of service metric threshold for each VM. Overall, loss is very low compared to the cluster overcommitments, as the deflatable VMs have significant unused or slack resources that were reclaimed without impacting throughput. These all show the effectiveness of the deflation-aware bin packing and proportional deflation policies. Now for preemptions, so VMs are preempted when the server cannot reclaim resources, even from deflatable VMs, due to too severe of cluster overcommitment. Now the proportional policy, while causing the most loss, did give the best reduction in preemption chance. So all deflation policies were able to nearly eliminate preemption risk at high cluster overcommitment levels of 40 to 50%. So this shows that cloud providers can be confident in their ability to reclaim resources with greater than a 99% chance at such levels. And interactive applications can be safely deflated without the risk of preemption or downtime. So for future work, the ability to adjust GPU shares in cloud environments is a promising research area, as more applications take advantage of accelerators for compute-intensive problems. So, investigating the noisy neighbor impacts of having many deflated VMs running on one physical server is important to prevent lost cloud time. And lastly, the impact of deflatable VMs on end users as they have to work with interactive applications running on these reduced resource machines. So deflation was originally introduced in Eurosys 19 and used application level deflation support. This work introduces black box deflation and doesn't need these application level modifications. And here we focused on evaluating real world viability using cloud application traces and interactive applications. So there are a variety of other VM overcommitment techniques, such as ballooning. Burstable VMs are a similar type of VM management that's more of the inverse of deflatable VMs. Transient computing and fault tolerance are common with tools like SpotWeb and SpotCheck out there, and large cloud virtualized cluster management is out there with things like VMware DRS. So in conclusion, deflatable VMs are an alternative to current transient offerings, but they fractionally reclaim resources instead of preempting VMs. Real-world data indicates that most applications work well within it. Hybrid deflation uses the best of hypervisor and OS-level overcommitment mechanisms and techniques, and its deflation and placement policies can dramatically increase cluster overcommitment for a small impact in application throughput. So thank you very much, and we look forward to answering any questions in the Q&A session after this. Thank you.